Good morning, everyone.
Good morning.
Morning.
Okay. Yeah, just this uploaded a link on Moodle where you should submit your spreadsheet for the last lab. Only a few persons have submitted. Please, if you haven't, please submit because we're about to download for marking, okay? All right, so today we want to look at the last part of our chapter 7. In chapter 7, we are discussing the rotational dynamics and how we use Newton's second law to understand the several dynamics to the motion of rotation. When we talk about rotation, we're referring to the motion about an axis, all right? So we have looked at a couple of terms, so we want to look at just the last part. But the last class, we saw the term torque, and we also emphasize that torque is actually the equivalent of force in linear motion, the same way force causes objects to accelerate in linear motion is the same way that torque causes objects to accelerate in rotational motion, okay? And then we looked at another term called tangential acceleration, which is actually the measure of the speed change of particle along the curved path. That is the tangential path that the particle takes when it's accelerating. Okay, so we're going to just bring those concepts together today and summarize into how we use the Newton's second law to understand the link between torque and angular acceleration. All right, so we saw in the last class that torque tau, we use tau, don't mind the way I'm drawing this, can be expressed in two ways. We can interpret it with respect to the force at the perpendicular direction to the radar line. You know what the radar line is? That line that is drawn from the pivot straight out to the particle. Then we'll have the action line, that is the line where the force is applied. So we interpret torque in this form, and we also interpreted torque with respect to the moment arm. Okay. So these were the two description or interpretation of torque that we learned in the last class. We also saw in the last class the relationship between the tangential acceleration and angular acceleration. This is your tangential acceleration and this alpha for angular acceleration. Okay, so I'm just reminding us because we'll be needing these two equations whenever we say we should recall this relationship, we should be on our fingertips. Okay, so the same way force causes acceleration in linear motion, torque causes angular acceleration. We have also emphasized that torque is the rotational equivalent of force. But today we want to actually look at the connection between torque and angular acceleration. And to do that, we have to start from the Newton's second law. So to better understand the concept of what we want to discuss, let's look at a single particle as shown in this diagram, a single particle that is attached with a rod to a pivot. So this is the length of the the rod, which is the R, and this is our pivot, and this is the particle M. All right. If torque is applied, we'll see that the particle will roll or will be set in motion. So assuming that the motion of the particle is taking this path, just to give us a positive direction, the counter, remember the direction of acceleration and torque that we saw in the last class, when it's going in the counter clockwise direction, it is positive, and when it's going in the clockwise direction, it is negative. Okay, so and remember we got that from our positive S axis. All right, so we assume that this particle is taking a positive acceleration. All right, we in our last class we defined something we call the tangential acceleration. So if we draw the path of this particle, which is this line you're seeing here, the tangential acceleration will point in the direction of the force. Okay, the force is applied to make this particle to move in this way. So the force that is causing tangential acceleration is what we have recognized as tangential force. And tangential force is called torque because that is the kind of force that causes acceleration causes angular acceleration or acceleration for particle taking a rotational motion. Okay, so we have the tangential acceleration and the tangential force and the mass all taking the part of that particle. Okay, so the tangential force causes the tangential acceleration AT to occur. So that force, actually what we mean by causing tangential acceleration is that it's causing the particle speed to change. We can also say it this way, that it is causing the angular velocity to change. So whatever twist we give to it, we are saying the same thing. Acceleration is changing angular velocity. That is, angular acceleration is changing angular velocity, and angular velocity is changing the speed. Okay, so when we say torque causes angular acceleration, you can put the word angular velocity to change or angular speed to change. So just note those ways we can twist those terminologies in any question. It can be in your objective, all right? So we can see another force also acting on the rod. We recognize this force as tension. We saw tension before in our catalog of forces when we discussed chapter 5, that is the application of Newton's laws, okay, which we brought about the description of the different type of forces that we can encounter. So we see tension is present in this case. The tension is actually the one causing the centripetal acceleration. How is centripetal acceleration different from tangential acceleration? Centripetal acceleration is directed towards the center of the circle, while tangential acceleration is taking the tangential part, which is actually the measure of the change of speed of the particle on the rotational axis, which is the tangential part of that axis. Okay, so having defined that, our tangential acceleration from Newton's second law of motion, which is F equal to ma, all right? F for force, A for mass, M for mass, A for acceleration. So making acceleration the subject of formula, A will be equal to F over M. We keep taking this concept to define new concepts when it comes to dynamics, that is the study of motion in the presence of the force causing it. Okay, so tangential acceleration therefore give us the tangential force over the mass for this particle. And that is what we have here. All right. So keeping that in mind, that tangential acceleration AT is equal to Fm. And we also saw in our last class this relationship that AT is related to angular acceleration alpha with this expression. So if AT is equal to this and AT is equal to this, we can actually equate these two, that Fm is equal to alpha R, which is what you have here. Okay, so from this expression, we'll make the angular acceleration the subject of formula. We'll divide by the coefficient there. So we'll have angular acceleration is equal to F over mr. So that is how we came here. All right. So this is actually an equation that linked the tangential force with the angular acceleration. So now we want to connect the angular acceleration to torque. Okay. So first we defined torque in our last class in two ways. It can be for moment arm and force, tangential perpendicular force, product of perpendicular force and R, which is distance from the pivot to the point where force is applied. Okay, so if we have seen the relationship of torque to be this, let us make the force subject of formula in this case. Force therefore will give us R. All right, so if force is T over R, not T, torque, tau, all right, tau over R, we can actually substitute this into this equation, okay, which is this one. So put F, here you see F, put this. So putting F there, we'll see that angular acceleration is equal to tau R dot, there's mr here, mr, which will now give you tau over mr squared. So this is how we got the relationship between tau and angular acceleration to be alpha equal to tau over mr squared. Okay, so remember we started this from the Newton's second law, and then we recall the relationship of tangential acceleration to angular acceleration to bring in our tau. All right, so it is this equation that established the relationship for a single particle, as we have seen in the diagram that we started the class with. We can actually extend this concept, which we have seen for single particle, to multiple particles for a rigid body. Remember what a rigid body is. A rigid body is that body that will not change shape or size when it's in motion. We saw the example of the bicycle wheel. We have another example like the rod we saw in this particle part. This rod itself is a rigid body. It's not going to change shape or size as it moves, okay? So we're going to use the understanding of what we've just derived to extend it to multiple particles on a rigid body. What will happen when we have more than one particle on that kind of system, okay? So let's see how we can also use from the understanding of Newton's second law to explain the rotation of multiple particles on such system. Okay, so we'll have another figure, which we have labeled figure R here, that the force on the rigid body exerts a tug about the rotational axis. And we've identified the rotational axis to be this point. Okay, so we'll have three masses or three particles with mass 1, M1, M2, and M3 to represent the three different particles. So M1 will have the distance from the rotational axis or pivot as R1, and the force acting, the tangential force, as F1. So we'll have M2 with R2 as well, and F2. Same applies to M3. We'll have the distance R3 and F3. Now, one thing to note here, which we have established in our last class, is that the angular acceleration for a system in rotational motion is always the same, no matter the distance of the particle from the pivot. We saw that in the very first example of the wind turbine, when we said, we also saw it in our checking understanding, where we put particle A and B, and we asked what will happen to the angular acceleration, and we all agreed in the class that it is actually the same regardless of the distance, because when you solve it, it will eventually even out to be the same value. Okay, so if we extend our understanding of net force, we have the net force of this system will actually be the force that will cause this object to rotate. Okay, so net force will be the summation of force 1, 2, and 3. All right, so the forces exert a net torque that will cause the object to rotate. So, and the object begin to rotate, it will cause it to have the angular acceleration. All right, and we also describe or emphasize that acceleration, the direction of acceleration in rotational motion will always take the same direction as that of the force. Okay, so this is what we derived in the first case. So if we make tau subject of formula here, which is the net force we are seeing here as tangential force, we will have this, okay, which is angular acceleration mass distance from the pivot square. Okay, so if this is our tau, so tau for M1 will be the M1 R1 square and the angular acceleration. This is coming from Newton's second law. Always remember that. Okay, so force gives you mass and acceleration. All right, so for M2, we have the same tau. M3, we have M3 R3 squared and angular acceleration. So the net force will give us, or the net force, which is net tau. When we talk about force as it relates to rotational motion, we are referring to torque, and torque symbol is tau. All right, so the net torque is going to be equal to the summation of the torque 1, 2, and 3, which is equal to the summation of angular acceleration, mass, and the distance squared. So we can actually rewrite this expression, bringing out the angular acceleration, and or we just put it in the sentence form, alpha summation M1 R squared to the number of events or masses that you have. Okay, so the fact that we brought out the angular acceleration also reiterates the fact that the angular acceleration is constant or the same for every particle in that system. They will have the same acceleration. Okay, so we see that this expression, we can actually make a statement that torque is directly proportional. Don't mind the fact that this sign of proportionality is about the same symbol like alpha, okay? So but here, I mean directly proportional to angular acceleration. And we can say that we brought in the constant of proportionality, which is mr mr squared. Okay, so we now have tau is equal to alpha times mr squared. So mr squared is actually the constant of proportionality in that expression. So now let's look at what we mean by that. To establish that torque is proportional to angular acceleration with mr squared as the proportionality constant. The constant of proportionality that we have seen there is actually what we call the moment of inertia. Okay, in the last lab, we'll always tell you to check that swing, that rod with the foam that cuts the ball, and you were checking a value underneath that we wrote I. You remember? How many of us remember? Did you? Okay, I know the Friday lab will happen today. So when you check the value I under that rod, it is the moment of inertia that we're describing here now. All right. A moment of inertia is described as the proportionality constant between the relationship of angular acceleration and net torque, and is I equal to mr squared. Okay, so if we have for multiple particles, it's going to give us I equal to summation of mi ri squared. I to stand for the number of particles you are analyzing. Okay, so moment of inertia for collection of particles, we use this summation to represent I representing the number of events or number of particles you're attending to. And the unit for moment of inertia is actually kilogram per meter squared. Now, one thing to keep in mind about moment of inertia, remember, whenever we discuss anything in rotational motion, we'll have its equivalent in linear motion, okay? Because it is actually the understanding of linear motion that we are extracting to interpret the rotational motion. We should also note that when we say moment, when we discuss moment of inertia and moment arm, it has nothing to do with time, okay? The word moment there stems from the word momentum, which means motion, okay? So when we say moment, we're actually referring to this motion in the rotational form. So from this understanding, we can actually express the Newton's second law for rotation. Newton's second law for linear motion is ma. For this, tau net is equal to this force, and moment of inertia is the mass equivalent in linear motion. So our mass in rotational motion times our acceleration. Okay, so where this is the expression of Newton's second law in the linear motion, linear, this is for rotational. Okay, so tau equivalent to force, moment of inertia equivalent to mass, angular acceleration equivalent to acceleration. All right, so this is our expression of Newton's second law for rotational motion. All right, so let's see how we interpret the moment of inertia. We have already mentioned that moment of inertia, first, you should have in mind that whenever you hear the word moment of inertia, we're actually referring to mass in rotational motion. So moment of inertia is the rotational equivalent of mass. Just like we have angular acceleration being the acceleration equivalent in linear motion, and tau force equivalent in linear motion. Okay, so let's see how we interpret that with the understanding that the mass, remember when we discussed mass and we're discussing linear motion, we mentioned that the acceleration actually depends on mass because mass has the tendency, the higher the mass, the more the tendency to resist change in velocity, which is the more the tendency to resist inertia. And what is inertia? The resistant ability of an object to change in velocity. If the object is heavy, it's not going to move on time. It requires higher force to initiate a motion. Okay, so we extract that understanding into this case also to describing the moment of inertia. When the moment of inertia is large, it will be hard to initiate motion, which is change in velocity. And it will be hard for acceleration to easily happen. Okay, so we should know this about moment of inertia. It is the mass equivalent. It also depends on the mass, which is what I'm trying to import from our understanding of inertia, the mass and how the mass are distributed on the rigid body. Okay, in this case, for this one, we want to look at the rim here. We have three persons standing at distance from the pivot. Okay, they are at the end. And this man has to move or initiate the tangential force on this pivot. Imagine a roller coaster sitting at the edge. And then remember the very first analogy we used in the last class where you have to push the door. Is it easier to push it close to the pivot or away from the pivot? So that's why this person is not coming here to start pushing. It's pushing from the edge. So you see that in this case, it has a larger moment of inertia, regardless of the fact that the particle or masses on this is the same as the one here. So it does not just, moment of inertia does not just depend on the mass, but also on the distribution of the mass about that rigid body. Okay, so here we see the moment of inertia is large. So it was hard for this man. This man has to exert high force to initiate rotation, which is torque. But in this case where they clustered together, the distance is small, the moment of inertia is small, it was easy for the man to initiate torque that will cause the object to rotate. Okay, so note this, moment of inertia depend on mass, and the distribution of mass on that rigid body is also the mass equivalent of force, and it has the symbol I. It is measured in kilogram meter. From this is mass kilogram dot radius meter then squared. So it is, each unit is kilogram meter squared and is given or expressed mathematically as the summation of mass, the product of mass and distance squared. So those are the information you should have. So if you're asked to define rotational motion, we have identified about 5 things. You should at least be able to drop 4 or 3. Okay. So let's see comparison of the linear dynamics and the rotational dynamics. We look at the variables in respect to, we're looking at it now in respect to Newton's second law, because that is what we use to understand the dynamics or the force that actually induce the change in velocity or acceleration in terms of linear, the change in angular velocity or angular acceleration in terms of rotational dynamics. So we'll have the net force is equivalent in tau, which we have already mentioned earlier. We see the mass, the unit. For the rotational dynamics moment of inertia, this is the unit. we see acceleration A measured in meters per second squared, but we see angular acceleration in this case measured in rad per second squared. Now bringing these three variables to give us the Newton law from F equal to ma, that was how we got A equal to Fm, all right? So from tau net equal to alpha I, we got acceleration here, angular acceleration to be the net of tau over linear moment of inertia I. All right. So this moment of inertia have been defined for some common shapes. And that's why in our lab, we just gave you the established or defined moment of inertia for that device you use for your experiment. So we'll have different equation representing different shapes. Okay, if you're asked any question about any of these shapes, the moment of inertia formula will be in the formula sheet, so you don't have to break your head to cram all this. All right, it will be in your formula sheet. So we arrived at this value by defining the point of the rotational axis, and at each different rotational axis we have different equation representing them. Okay, so we have, that is how we have the established formulas for so many shapes, not just limited to the one we have in this chart. Okay, so how do we solve problems that relate to rotational dynamics? We have been solving problems that relate to rotational dynamics before, but we also imported the approach of what we saw in chapter 5. But in this case, the only difference is that in chapter 5, we're still using the particle model. We'll have to summarize all the object to be one particle. We have already said at the beginning of this class that we cannot do that here because of the dynamics of the rotation. We said that in a rigid body, three types of motion can happen: the translational, the rotational, and the combination. So we are not able to just import the particle model idea, but we use that idea, we extend it. Instead of making just a particle, we identify the object as a shape, okay? So you can actually make a virtual representation of the object as a shape. Then all other steps applies, all right? So we'll have, when you're given a problem, you make the model. In the other case, we say define the rigid body, okay? The body diagram, free body diagram. But in this rigid body, you have to represent it like a shape, okay? Make a simple shape, then identify the rotation. Where is the force acting on? What's the distance from the pivot? Okay, so that you can clearly have an overview of what the situation is. Then you can now develop from the question the formula to use, because we have different formulas with different relationship depending on the parameter provided in the question. Okay, so you identify the axis about the object about which the object will rotate. You identify the forces, the tangential force, and if there is another kind of force like we saw in the case of the one single particle, the tension force, you should also be able to identify that. We're not going to present any force beyond what beyond the type of force you've seen in a catalog of force, so it's nothing strange. All right. So we now use the Newton's second law expression, which is this for rotational motion. And then we can now use a rotational kinematic equation to define the position and velocity if need be. The same equation applies, right? The only difference is in the terminologies. where you have to say acceleration for linear, you say angular acceleration for rotational. Okay, so it's nothing strange from what we used to know. So let's quickly look at the constraint due to rope and pulley. And how do we use this to interpret rotational motion? We'll see that this rim here will bring a constraint to or define the motion of this rope, okay, and the direction of this weight. So that's what we simply mean by constraint due to rope and pulley, okay. So we'll have the motion of an object that is tied to this rope must match the motion of the rim. So if the rim is going in this direction, this object will go in this direction. The rope will go in the same direction. So the rim constrains the motion or the direction of the rope and the weight on it. If we reverse this direction, what happened to this? We'll be lifting this weight instead of dropping it. So the motion of the rim defines or constraint if we are lifting a rope or dropping them. So from applying our understanding of the velocity, which we saw earlier to be equal to angular velocity r, but we have defined our r here for the rim as capital R. So we'll have the rim speed v is equal to omega r, okay? And we also saw the relationship for r, if you remember when we saw v equal to 2 pi f, yes, rf. When this completes one full revolution, it will give us 2 pi r, which is circumference of a circle, change in time, t, which we converted to be f, okay? So we'll have the rim acceleration, which we can call the tangential acceleration on this point, to be this relationship. I've seen this before. This is defined as capital R. So we'll have the rim acceleration to be alpha R. So the same thing we wrote here is what we represented here. The velocity of the object, this object will be expressed as this, and the acceleration expressed as angular acceleration, product of angular acceleration and distance. So we see how that the rim constrains the motion direction of the weight and the rope for a non-slipping rope, okay? So the weight is not just pulling the rope off the rim. It is actually being defined as the motion that the rope takes round that rim, okay? Which is the motion of the rim defines the motion the rope takes round the rim. So I encourage us to check the example 7.19 of our text to better understand this. So let's look at the very last part, which is the rolling motion. Rolling motion is a typical example of a combinational motion, which is the combination of translational and rotational motion, which we saw as the third type of motion that a rigid body can take. All right, we saw separately translational, then rotational, then a combination of both. So if we have, for example, that kind of rim we saw earlier for the pulley and the rope, if we bring just that rim out and we position the rim here such that a point on that rim is resting on this platform, and we make that rim rotate. This point will rotate upward. Then when it touches the platform again, it has completed one revolution. And we can say that, remember, velocity is change in distance over time. And then you remember when we derived the change in distance, which is one revolution, which is the circumference of a circle. In this case, we used big R because we define our big small distance as big R. And the time, which is the time taken to complete one revolution, which is actually period. And that was how we got V is equal to 2 pi RF. Okay. So we see that this relationship also applies here, right? So the combinational motion of this object rotating about its axis and at the same time making movements along a straight line trajectory. So we'll have the rotation part and the translation part. Okay. One is happening about the axis, one is translating, making movement. This is translational, while this is rotational. So we see that at the point, V is always pointing towards the direction of the motion. So the object is rolling and has taken one revolution without slipping. All right. So let's see how we combined the translational and the rotational to give us the rolling, which is the combination of the motion. Okay. So the combination motion, we combine the rotational. There's a force. Remember when we saw the linear situation where you have to take a walk, the force of friction acting opposite to the force of your motion. So the same thing happened here. At this point, we see this acting opposite to this with the same magnitude, but the negative telling you the different direction. Okay, so this force will act on this and it will cancel out, and that's why we'll have V here to be 0. The one in the middle is not changing for the rotation, so V plus V remain the same magnitude, which is V equal to omega R. But this one is vector summation, okay? So V added to this will give us the length 2V, which is 2 omega R. So we see that the point at whenever the point is resting at the base, we are having at the initial V, which once it becomes, once it starts translating or rolling, it combines to give us V equal to 0. While the point at the top is going to be double the V. The one at the middle remains constant. Okay, this is important because we'll be applying it to the example we'll be seeing now. Okay, before we take that example, let's quickly check our understanding, and I expect us to quickly answer these two questions. You have 1 minute to do that. We'll have 5 minutes to look at the example and we'll call it a day. So I want to start seeing response to the two questions before you. I need everybody in the class to participate, please. It is important that we participate. I'm not seeing response yet. Can you see my screen? Can you see the pool launched?
Yeah, it's there. It's hard to read it well with the talking, so.
Oh, okay, sorry. Okay, I have 6 persons. You're here to respond. The remaining 6 persons, we're about to end the pool. It means out of 24 persons in class, 6 persons are inactively participating, and there is call for participation. This question is not about the right or wrong. I want you to express how you feel to the question. I just want you to participate. Whether you have the question right or wrong, you have your score for participating in class. So I have 6 persons now, okay? Now 4 persons that are not responding, so it means they are inactive in class. Interpreting it means they just logged on and left. All right, so we end the pool now. And then we'll talk about the result of that pool later, if we have the time, okay? So let's look at an example in the next 4 minutes. You are driving down the highway at 65 miles per hour, which is equivalent to 29 meters per second. And you have the radius of your tire to be 0.3 meters. The first question says, how many times per second does each tire rotate? This simply means instead of asking straight out, what is the frequency of your tire? We just put it in words or define the frequency out. Frequency is the number of revolution per time. So when we said how many times will it rotate, we're asking about frequency. So from the question, we know that we can actually use the relationship V equal to omega because it's rotational over R or small r. So we use big R because we're just looking at the example of the rim as a kind of representation of your tire, okay? The radius is given and the speed is given, right? So we'll make this the subject of formula to get what the angular acceleration is. So the rim speed is what we got here. So from 29 divided by radius, we'll have the angular acceleration. So from the angular acceleration, from V equal to that is angular acceleration, V equal to 2 pi RFT. Okay, and remember we established the relationship between as angular acceleration R. So equate these two. Okay, this takes care of this. So equating these two, we have W will be equal to 2 pi F. So making frequency the subject of formula, we now have W divided by 2 pi in rad. So that's how we got this. So we have found out W to be 97. 2 pi is constant. We have 15 rev per second. So the frequency of your tire is actually moving at 15 revolution per second at this speed. Okay. And the second question says, what is the speed of the point at the top of the tire? The point at the top of the tire from the analogy of translation plus rotation will give you what? Twice the speed. But at the base, it's going to be 0. So we simply said for the question B, from that analogy of combination motion, we have that V is twice, that is 97. It's twice the velocity to give us 58 meters per second. So we just did 2 times V, okay? And we got 58 meters from V equal to RW, make V the subject of formula here, and times it by 2, we'll have 58. Okay, so we'll end our class here. So let's see. Let me launch the result of the pool. I can't find. Oh, I've downloaded it. I can't launch it again. Okay, but in that pool, the second question, yep, some of us responded that for the first question, I just give the answer. The answer is C. Now, we said something about moment of inertia. When you just define moment of inertia as mass, the statement will make sense. Okay, we said that we kept emphasizing moment of inertia depend on the mass and the distribution of the mass on the surface or the rigid body. Then for the second part, we said that some of us picked, the answer is B, many of us also picked C and D. So let's interpret it this way. A net torque applied on an object causes, if you replace the statement, mass, moment of inertia of object to change. Does force cause mass to change? Force does not cause mass to change. So the answer cannot be C. If you replace the word moment of inertia with mass, for example, in terms of linear, force does not cause mass to change. But what we simply mean by net torque is simply saying force applied on object will cause mass to change. No, force applied on object will cause object rotation to rotate at constant speed. No, you cannot say unless it's defined as the motion. D can happen, but D is subject to the definition of the question. We did not specify that the object is going to take a uniform motion. Now, we have cases where the net torque or the force will be equal to 0. Acceleration automatically equates to 0 in that case, which means that the angular velocity is constant. It's a uniform motion. So that happens when there's a uniform motion. So force does not cause linear acceleration. When we use the word net torque and we say linear acceleration, it does not match. A would have been the answer as well if we defined the word there as angular acceleration. So the linear is what changed the option from being A. Okay, so those are the tricks about the question and language that we should use. We used net torque, therefore we cannot relate it to linear. We can always relate it to angular, all right? Okay, that's the end of our chapter 8. I'm going to be posting something on Moodle about the lab to answer question 3 or so. I'll specify it in the news forum, so watch out for that. All right, are we all good?
And you said you wanted us to submit the Excel sheet somehow, you said?
Yes. There's a space already on Moodle for you to do that. So just upload your Excel sheet. We'll be downloading the final download at the end of today for marking. Please upload your Excel sheet for marking. Okay.
And for which lab was that one for? The most recent one or?
No, the last one. We didn't use Excel for this recent one.
Okay.
The last lab where we had to measure acceleration due to gravity. Yeah, wasn't no, it's not acceleration due to gravity. What was the last lab?
It was a drag lab.
Yes, the drag lab. So, okay, I have some statement in chat.
All right.
Okay, yeah, drag lab.
And you
All
said
right.
you said there was a place to submit the Excel sheet already?
Yes, you will see it on Moodle. I think it's under the lab section of Moodle. I'm going back there to see.
Yeah, it's under the lab section. It's labeled as drag lab spreadsheet submission.
Yes. The last item second to the last item under the lab section of Moodle. Okay. Thank you so much, everyone. Do have a great weekend.
All right, thanks. Bye.
Bye-bye.
Hi, I have a question.
Okay.
For this lab, do we need to hand in like what we usually hand in, like the purpose and stuff like that, or is it just the drag sheet and the what is it called, the questions?
The result and the question, I'll announce that in module so that we'll all be on the same page at the end of today. So look out for that, okay? But it's just going to be the result and the questions. So we're trying to reduce your workload. There's a lot to read now, and we're approaching exams, so you'll not be spending so much time doing lab reports. All right?
Okay, sounds good. Thank you.
Okay, all right. Okay. Thank you, everyone. Have a great weekend.